Hi, I'm Camille, and we are here on the Who Gives the Flood channel. I have Stoka Brown here, and we are going to talk about flooding, specifically for this episode in South Louisiana. We know that's a hot topic in the area, and I am here to ask Stoka questions, and he is here to educate us, the public, on flooding. So I will give it over to the brains of the operation, Mr. Brown.
Thank you. I'm Stoka Brown. I am a principal at CSRS and the Water Resources Practice Lead. I have been focused on identifying, estimating flood risk for 10 plus years, going on close to 15. And one of my focuses is about communicating flood risk. And as Camille said, it's a hot topic in Louisiana given the recent flooding events. And what I've developed are tools and techniques that help communicate that to the general public that don't necessarily understand everything that goes into flooding and hydraulic models and looking at technical data. We can disseminate that down into maps that are more easily understood. So today we're just going to step in at a high level and talk about some of the different tools that enable us engineers to calculate and estimate flood risk. And then we'll also look at tools and advances that allow us to better communicate that to the general public. And we'll actually get in and look at some of these things. So I'm gonna pull up a general presentation that I give that just kind of looks at an overview of hydraulic modeling and applications. So hydraulic and hydrologic modeling. So understanding what these two things are is a start. Hydrology is the study of rain from the clouds down to the ground and understanding where that rain is going to go once it hits the ground. Is it going to infiltrate into the ground, the grass, or sand, the soil? Is it going to flow over the concrete and into a roadside gutter? Is it going to flow off the roof of your house into a gutter and then flow in the ground to the ditch? All that eventually leading to a larger ditch, a larger channel, eventually to a lake or the Gulf of Mexico or the ocean. Hydraulics is the study of that water. Once it gets to a channel or a river, the study of that flow in the channel, and really we're focused on how high does that water get once it's in the channel.
And for clarification, you do both of those?
I myself and my group mainly focus on the hydraulics. So once it gets to the channel, how high does that water get? The advances in technology today really start to blend those two, because you'll see in a bit, the 2D models, we essentially have rain on top of the model mesh, and the model will help define where that water collects. So in today's modeling, the two are sort of combined.
Gotcha. And when you say modeling, what exactly does that mean?
So it's a computer simulation.
Okay.
So we use software. A majority of the industry uses HEC RAS, also commonly referred to as HEC-RAS, and it is essentially a computer model. And I can why don't we save that, and I'll show you what the model looks like.
So when you say a model, it's a computer program.
It's a computer program that simulates it raining on the ground, collecting to the channels, and helping us estimate how high the water gets.
Gotcha. That's why I'm here, friends, to ask the questions to the engineer for the rest of us to understand.
Yes, thank you. Very valuable. Okay, so here's an example of just hydrology. So understanding how much rain fell where. This is showing the peak, the total rainfall values depth that occurred during the 2016 storm, the August 2016 storm in southeast Louisiana. And we're seeing depths greater than 20 inches. I believe the largest depth in the 2016 flood was about 34 inches in Denham Springs. And so one of the important things to note about certainly this map and in general is that it's not going to rain the same amount everywhere. Now, if you're just looking at your neighborhood, then the whole neighborhood probably gets the same amount of water. But as you start getting larger and larger areas and start studying watersheds such as the Amite River Basin that spans hundreds of square miles, you're not going to get the same amount of rain everywhere. So it's important that when we build these models, we simulate a rain event that actually happened and compare the model results to what we know happened on the ground, so we can make sure that the models are accurately replicating the past event, so that when we use the model to help understand potential future events, we have more confidence in that it's going to give us something that's more or less accurate.
Okay, so
Which we call calibration, model calibration.
so you take the information from a big storm event and compare that to your computer program,
Yes.
and they should both match up similarly.
More or less. So what there's, and we don't want to get into too much of the details
No,
here,
you
but there are
don't.
certain parameters within the model that we can adjust within reason. So if
Okay.
you think about water flowing across a concrete surface, there's not a lot of resistance versus water flowing across, a heavily vegetated area. There's a whole lot more resistance. So that resistance factor is something that we need to adjust in the model. Now we start off with based on what's on the ground, right? We know if there's concrete on the ground or if there's brush on the ground. But there's still, it's not an exact science on what the actual value of that resistance is. So there's some things that we can adjust to understand, adjust it until it meets what we know happened.
Gotcha. Okay, thank you.
You're welcome. So here's an example of the May 2021 rain event. And on the left side of the screen here, we're seeing the rate of rainfall. This is the depth per hour. On the right side, this is showing accumulation. So this is just an example of how we can pull information from NOAA, NOAA, to understand how much rain fell when, because it's important that we put accurate rainfall information into the model so that we can have a better comparison on where it flooded when.
Okay.
So continuing on advances in technology, LiDAR information, we would not be able to do what we do without LiDAR. So LiDAR is light detection and ranging. Essentially, they fly a plane, a helicopter, or today they fly a drone. And it's got a sensor, a radar sensor, a light sensor, I guess you would say, and it continuously shoots down to the ground and bounces back. And so based on the timing of that, we understand the elevation of the ground across large distances, where we no longer need to have survey crews out there putting the stick down trying to understand. So it's a much cheaper way for us to get an expanse of what the elevations are on the ground.
Cool.
And so here's an example I have of LiDAR. You're going to see this a lot in these presentations, so I want to get you used to the color scale.
What is this area?
So this is in Ascension Parish.
Okay.
And so the higher elevations in this LiDAR are in the grays, and then sloping down to the reds, the oranges, the yellows, the greens, and then lowest is the blues. Okay, and so for anyone familiar with this area, this is the Bluff Swamp area, Spanish Lake. This is I-10 headed towards headed towards New Orleans this way, headed towards Baton Rouge to the north. And this is the Amite River here on the far right, and Bayou Manchac here on the top. So this was LiDAR collected in 1999, and so I'm going to kind of flip back and forth because this is LiDAR that was more recently collected in 2018.
Okay.
And as I flip sort of back and forth, we can point out a couple locations, and you can see that there was a development that occurred there, right? So they're going to increase the ground. They've got a detention pond in there, and so it's important to understand that as technology advances, if we were only using 1999 to build a model from, we wouldn't have anything that occurred within the last close to 30 years, right?
Yeah.
So having the more recent LiDAR gives us a better, bless you, has a better representation of what's on the ground. However, 2018 is the latest LiDAR for Ascension Parish, and now it's 2024, so we're 6 years past now.
How often is this LiDAR data collected?
So the LiDAR data is collected probably every 10 to 15 years. The state of Louisiana at least has said they would like to collect it every 5 years, certainly within every 10 years.
So is this something that our tax dollars pay for?
Yes.
LiDAR? Okay. And
it can be collected privately, but it's expensive. So, and especially on a large swath of, like if you're talking Louisiana, no private entity's gonna likely put in the amount of money to collect that large of an area. So it's certainly using tax funder dollars, and the benefit of using tax funder dollars is that it's free for anybody to go and grab from the internet. And I'll share a link or a call out on the screen if we can get that to work. On where you can best find that latest LiDAR data and information. So the second thing that you get, not only do you get a more recent representation of what's on the ground with more recent LiDAR, you also get higher resolution, better quality of data. So here's a zoomed in area of the 1999 LiDAR, and then here's the 2018 LiDAR. It's like you put a pair of glasses on, right?
Right.
So if I go back, here's a roadway, and this is a railroad, and then we've got a stream here, so we can see we've got a much more accurate representation of the elevations of that road, the elevations of this railroad, and even some of the lower elevations of this channel. Now, it's important to note that the LiDAR technology does not penetrate below the water surface. So, so if the day they flew it, whatever the water level was, it's not going to get any elevations below it. However, in the hydraulic computer models that we use, we need to know what's below the water, because that's important for a lot of that water to flow downstream. So we do have to go in and provide some traditional survey of the channel cross sections, and then we merge those two data sets, the traditional survey with the LiDAR, to create what we call a topobathy data set, and that's what is used within the hydraulic model.
And when you say traditional survey, you mean like a human going in?
Yes, a survey crew.
Stick.
So a human with a stick, or a total station, or a GPS station. There's that technology has advanced also, but yes, it needs to be sort of a person crew going out and collecting cross sections of the channels.
Gotcha. Computers can't do it all.
No. Maybe one day, but not today.
Not today.
Not today. Okay, so those were some of the advances in technology related to what we put into the hydraulic model. I'm going to talk a little bit right now about the advances in the hydraulic model itself. So, 10 plus years ago, the standard in the industry was one-dimensional modeling. So I've got on the screen here an example of a 1D, one-dimensional model. And essentially what that means is water is able, the computer model only computes water going in one direction, so either upstream or downstream. So it's important.
How awful.
For a 1D model, Look, so I want to make sure that the 1D models certainly have their place.
Okay.
So if you're like up in Colorado, or you've got an area that has a lot of relief or slope, and water is very confined, you know exactly where it's going to go. There's no reason that a 1D model isn't good enough for what you need, right? But as you'll see in an example I'm going to show you, when you get into very shallow sloping areas like South Louisiana, it's very important that we have a two-dimensional model. And so in a one-dimensional model, we have to define where that channel is, which you see in the blue line, and then we define the cross section, or how do I explain cross section? What the water sees as its ability to flow downstream. So if you were the water standing in the channel, you know, what elevations on the ground do you have to flow downstream? That's essentially like a cross section. And maybe to help with that, I don't have it on the screen here, but I'll put an example of a cross section on the screen to help everybody understand that.
Okay.
So there, water's flowing upstream and downstream. Okay, so 2D modeling, two-dimensional. Water can flow in two directions, right? Upstream, downstream, to the left bank, over the right bank. Essentially, we lay I almost call it like a carpet. Essentially, you just kind of put a carpet and you drape it over the surface of the ground, and it's going to take the slope of the ground. Instead of having just one cross section that represents one section of the ground, we've got elevations of the ground throughout the whole watershed.
Okay. Do you ever anticipate there being like 3D hydraulic?
There already is 3D hydraulic models.
Okay.
They're not necessarily needed when you're talking about flood risk. Certainly, unless you get all the way down to the coastline.
Okay.
But even then, strictly looking at flood risk is not that necessary. A three-dimensional model is essentially going to allow flow in the vertical direction, right?
Okay.
So the only, horizontal, up, down, left, right, that's the two-dimensional models. 3D allows flow in the vertical direction. But if you think about flooding's never flowing, the water is never flowing up or down. It's always really just kind of flowing across the surface.
Okay.
If you start getting into coastal and like salinity and different densities of water and a salt wedge, this past year there was a lot of stuff in the news about the Mississippi River salt wedge because of our drought and the lack of fresh water coming down the Mississippi River. The Gulf of Mexico salt wedge was able to move as far up into the Plaquemines Parish and almost as far up in the Orleans Parish, where when people were pulling water from the Mississippi River, they were starting to pull salt water, which was an issue.
Okay.
So that salt wedge is more dense and it flows on the bottom of the surface. So if you're trying to model those types of dynamics, 3D is important. But for the sake of flood risk and flood risk estimation, it's not, three-dimensional is not needed.
Okay.
So I'm going to give you an example of where in the city of Central, which is where we live, this two-dimensional modeling was extremely valuable. Okay. So I'm going to point out a couple features here. Here's another picture of LiDAR. Like I said, we're going to show you LiDAR on the screen a lot. Refresh your memory. The grays are high. Sloping down to the reds, the oranges, the yellows, the greens, and then the blues.
Or the low areas.
Or the low areas.
The blues, the lowest.
Blues, the lowest. So we can see some streams in the blue here. And then we can sort of see what we call this meandering pattern. Okay, so it's the stream not just going straight, it's curving and it's meandering like a snake. Okay. This is the traditional historic channel path of Beaver Bayou. Okay. However, at some point in time, somebody wanted to change the location of that stream, that bayou, right? It happens all the time. I see it constantly as we're going out doing studies, trying to figure out what flooding problems are. Somebody doesn't want the stream there because they want to do something else with the land, so they cut the ditch in a different direction and reroute it.
Okay.
In this case, they rerouted it through this ridge. So we've got a natural ridge here. You see the natural higher grays and reds.
Mm-hmm.
They cut that through the ridge,
Mm-hmm.
made this beautiful 90-degree curve, which is, 90-degree curves are not hydraulically efficient. And they cut it, and then we've got this man-made ridge, also known as a roadway.
Okay. Yeah.
And it traverses, right, roads. We don't want them to flood, right? So you're
Okay.
gonna elevate them. This road is perpendicular to the flow path of the water. So elevating something perpendicular to the flow path of the water is almost like creating a dam, right? It's more or less
Okay.
creating a dam. But we put culverts or
I was
bridges.
gonna ask, is there like something for it to flow
Yes.
under the road?
There is.
Okay.
That's why we put culverts and bridges at certain locations in the road,
Mhm.
mainly certainly where there's a channel,
Mhm.
right?
Okay.
And this is where we have an issue here. So because they rerouted this channel,
Mhm.
and whenever they came and built this road
Mhm.
with a 1D model mindset,
Gotcha.
the
yeah.
engineer's gonna assume all the water is gonna come through the channel. So that's where we're gonna put the
Right.
culverts or the bridge.
Uh-huh.
Well, whenever we put a 2D model and built a 2D model and understand where the water was flowing for this watershed,
Mhm.
so on the left side here is an example of output
Mhm.
from the 2D model. So here's the start of communication of flood risk
Right.
from
Okay.
the model and technology that we have, okay?
Okay.
On the screen here, we've got the satellite imagery
Mhm.
helping us understand where we are.
Mhm.
And we've got these different shades of blue. These
Okay.
different shades of blue represent flood depths.
Okay.
The darker the blue, the deeper the water,
Okay.
okay? And we've also got these, we call them flow lines or flow tracers. Okay.
Gotcha.
These are helping us understand where the direction of water flow. Okay, so for instance, here's that main channel,
Yeah. Okay.
and we see water going down this channel,
Mhm.
but we also see water coming out of the bank and flowing in the direction where I pointed out earlier, we have that old historic channel. Okay, turns out 75% of the water in the 25-year storm
Mhm.
is flowing out of this main channel and collecting in the area where it used to flow. However,
Okay.
when they built the roadway, they didn't account for this. So
Uh-huh.
all this water is coming to, now they knew water was flowing across here because there's a small channel,
Mhm.
but they didn't assume that 75% of the bayou was gonna have to come across the roadway at this point.
Mhm.
So it backs up and we can see those dark blues up here.
Mhm.
And it's certainly flooding the roadway. That
Mhm.
is the only one way in and out of this neighborhood.
Oh, wow.
Okay, and it
okay.
even is flooding certainly the property, the yards,
Mhm.
and maybe getting into some of these houses.
Okay.
Okay, and so what we can do is, after we understand where the water is actually going and what the problem is, we can propose a solution.
Okay.
And what the great things about the hydraulic models is we can simulate on a computer what that solution would create before we go and build it, right? Because
yeah.
we want to make sure, we want to understand, okay, well, if we do this, what are the actual benefits?
Mhm.
And also important to understand, well, what else way might we be impacting?
Right.
Because we're moving water from one place and putting it somewhere else.
It has to go somewhere.
It's got to go somewhere.
Okay.
If we had an enormous evaporator,
Uh-huh.
everybody's life would be a lot easier, but we don't have that technology yet.
Okay.
So the solution here would be, all right, let the water cross the road where it's collecting,
Mhm.
right?
Okay.
And so here is the simulation of us doing that. So this, on the right side of the screen here, is showing a bridge at that location. And so if you kind of look across the two,
Mhm.
left and right, you see there's not as dark a blues.
Mhm.
And the flow direction of the water is more north to south, which is the general direction of flow for this watershed. So, and then we can see, the water is not some of these properties are not flooded anymore based on the blues, and so, but this roadway still looks like it's a little flooded. And so that's another communication piece of how we can sort of quantify the benefits from proposing these projects.
Okay.
I also want to talk about another piece of information we can get from these models. It's not as flashy or as easy to understand as an aerial image looking at flood depths, right? So we're back to some of the traditional communication of flood risk where you're looking at a hydrograph. So this is a hydrograph. So this is understanding the depth of water on top of the roadway at this point through time. So it rained, the water's flooding to it, the water's now on top of the road, and so this royal blue line is existing conditions in the 25-year storm. And so it's getting up to 1.5 feet deep on this roadway. Okay. And so with the bridge in place at this location, this is the resultant water depth on that road when you put the bridge there. So it's reducing the depth of water on that road by a foot.
That's really impressive.
So a huge benefit.
Yeah.
What's equally as important is understanding how long that road is flooded. And we're going to talk about a 1/2 foot depth. So the federal government sort of identifies that a roadway is impassable, is considered impassable if it's greater than a 1/2 foot depth. Okay. So essentially the road is closed. So
turn around, don't drown.
Turn around, don't drown. Right. We'll have a whole episode about that, I think. So if we look at this one road in and out of a neighborhood of more than 100 residential community, in existing conditions today, they are, the road is closed 16 hours. And with the implementation of this flood risk reduction project, it's only going to be closed for 3 hours. So a significant benefit of, number one, evacuations, getting out of there. Number two, emergency response, having to get in and help anybody that needs help. Right? So that's just a little bit about the hydraulic models and how they are better at estimating flood risk, and a little bit about the communication of that flood risk.
Okay. And a few questions before we wrap up. In your line of work, are you able to pinpoint an area? Like, let's say I wanted to look at my house. Are you able to pinpoint an area on a map and say, yes, with these certain things happening, your house would flood, or no, it wouldn't flood? Are you able to pinpoint specific areas?
So that's a great question, and like every engineering answer, it's not a yes or a no. Okay. It depends. Okay. So it depends on if there's a study or a model been developed for the area that you're interested in.
Okay.
There have been, and there are different levels of studies, right? Down from, and even a study could be somebody who's lived there for 50 years can help tell you what's flooded when.
So you'll take people's
absolutely
I guess experiences.
People's experiences are sometimes invaluable because if we don't have data about what happened in the flood, that's the only information we have to make sure that the model is replicating what actually happened. A model is only good if it's somewhat accurate, right? If it's accurate. If we build a model and it's actually saying something flooded and it didn't in a storm, then it's not useful. So models are only as useful as they are
Every city doesn't have a model built, I'm understanding?
Correct.
Okay.
So probably the widest data set, although there have been recently within the last couple of years, new data sets come aboard that
Mhm.
have national coverage for the United States. even.
Okay.
Before that, the standard is FEMA. FEMA
Okay.
flood maps.
Mhm.
FEMA flood zones, Zone X,
Mhm.
Zone A, Zone AE.
We'll have an episode on flood zones
on,
as
on
well.
all of that. And my computer just died, so I cannot go. But I'm gonna throw some screenshots up, I guess, for the
Okay.
sake of people to see an example. We're not gonna get into details, but an example of FEMA.
Mhm.
But yes, you can go in and look on FEMA's website. Go to the national flood layer
Mhm.
and put in your address, and it'll go to that location
Mhm.
in the GIS viewer, and
Okay.
you can understand what FEMA at least is telling you that your flood risk.
Okay.
Now, we'll get into the details in another episode, but there have been a lot of misunderstanding about the FEMA maps
Okay.
because the FEMA maps were created for flood insurance rates. It's a flood insurance rate
Okay.
map, right?
Uh-huh.
A firm, FIRM.
Uh-huh.
They were meant to generally identify what properties need to have flood insurance and which ones don't.
Mhm.
If in the whole grand scheme of things across the country,
Mhm.
if some properties are in, some properties are out, from an insurance perspective, it's still a good system,
Mhm.
right? But from an individual flood risk perspective,
Mhm.
it's not a good system.
Mhm.
It was never originally meant to be used to quantify what a single property's flood risk is.
Okay.
Just a general understanding of should you get flood insurance or not.
Gotcha.
Today's tools are much better at quantifying individual flood risk, and we have some of those tools today. There are some flood map, I know, is one
Mhm.
company that provides flood risk estimation across the country.
Uh-huh.
Fathom also produces a similar data set.
Mhm.
So those are national. FEMA, flood map, it's MAPP,
Mhm.
and Fathom. Those are national data sets that can be used. But if your community, like the City of Central, East Baton Rouge Parish, Ascension Parish, a couple I know that we've been involved in across South Louisiana, if that community has their own hydraulic models, then you've got that additional data set.
Okay.
And they more or less they put some layers online similar to these other national maps that you could go in, put your address, and sort of understand what your flood risk is.
Okay. And last question for this episode. What would you say is the best way for us, the public, to make sure our homes don't flood?
Gather as much data and information as you can.
Before you buy a house?
Before you
Or
buy a
decide
house.
where to live? Okay.
Yeah. So, I can't say that enough. You don't know what you don't know
Mhm.
unless you go and try and find that information. Contact the local floodplain administrator. Every community has a local floodplain administrator that is going to know the best data sources out there to help quantify what flood risk is. Or if you know civil engineering companies that have hydraulics engineers, reach out to them. Maybe see if they can help you point into directions of models, flood maps, other data sources. But don't just go. There's so much data available today that you should not just go buy a home or decide where to live before trying to find some flood risk information.
At least in South Louisiana.
Certainly in South Louisiana.
Maybe
I mean,
other
look, it's
places
gonna
are
rain.
okay.
It has the possibility. It has the possibility to flood wherever it rains,
Mhm.
and it can rain everywhere,
Uh-huh.
right? Depends on how much rain falls within a certain period of time, and if there anything blocking that water to flow downstream before it gets into your house. So it can flood anywhere.
Mhm.
The likelihoods are different.
Yes.
The probabilities are different,
Mhm.
and there's a lot of data out there to help understand what those probabilities and possibilities are.
Okay. And that's it for this episode of Who Gives a Flood. We'll be doing this weekly or bi-weekly to give the public information about flooding and to how to prevent your homes from flooding. Thanks for joining us.
Thanks, everybody.